This is another diviner-related talk. And the idea is pretty simple, but I think it has some pretty potentially interesting and subtle implications for our understanding of cold traps and their distribution on the lunar surface. So we know that the lunar surface is extremely rough, and we also know that it's extremely insulating. And so I'm going to argue in this talk that these two facts combined mean that the minimum size of cold traps on the lunar surface is quite small, and therefore we should expect that these small-scale cold traps, and by small scale I mean less than a meter, or at least less than the size that we can distinguish with temperature measurements like diviner, or with models utilizing topography from LOLA or other scales on the size of hundreds of meters, that those could represent a significant fraction of the lunar surface. So the methods that we've used here are to use one-dimensional temperature calculations similar to what you've seen before from the other diviner talks. These have been sort of extensively validated with the diviner data themselves. And what we're doing is we're basically taking the surface roughness, not only from LOLA topography, but also deriving the surface roughness at smaller scales from the diviner data itself, using thermal emission phase functions. I'll talk a little bit more about that in a minute. And so the way that we do the surface fluxes is by using the slope-dependent surface illumination and infrared fluxes, which is sort of illustrated in this diagram on this plot here, where we account for the thermal infrared radiation coming from the surrounding terrain, which depends on the angle of the local slopes. And just for the purposes of this talk, although it's not necessary, we're going to use a simple set of criteria for surface ice stability, and this is just a standard 100, it's 110K, we're choosing 106K in this case. And then the cutoff for buried ice is based on work that Norbert Schorghofer has done, which shows that at about 145K, ice buried beneath a surface lag deposit of a meter or so is stable on geologic timescales. That's for the mean annual surface temperature. So the two cutoffs are 106K for the maximum temperature and 145K for the mean annual temperature. So the basic idea is that on the moon and other airless bodies without an atmosphere, you basically can maintain these massive thermal gradients. And the thermal gradients can persist on relatively short length scales if the thermal inertia of this material is low enough. And so what we observe on the moon is directly illuminated surfaces tend to be around 400 Kelvin, but then the colder shadows can be much, much colder. And we can actually measure this with diviner. So the way that we do this is by measuring the brightness temperature of the surface at grazing incidence angles at two different wavelength bands. And so the shorter wavelength band picks up the warmer temperatures, and the longer wavelength channel picks up the colder temperatures. And the difference in the brightness temperatures that you measure is dependent on the surface roughness. And that's just illustrated here for these two different hypothetical surfaces. You can see the big difference between these two diviner measurements in the bottom plots. So when we actually match the model to data, we find best fit RMS slopes in the range of about 20 to 30 degrees for scales smaller than the diviner footprint. So the typical diviner footprint is about 250 meters. And so what this is measuring is really the surface roughness on all scales below the diviner footprint. So every scale over which a thermal gradient is maintained at these solar incidence angles is captured by this trend. And disentangling exactly what scale dominates is somewhat complicated, but basically because surface roughness tends to increase with decreasing scale, this means that we're mostly sampling the smallest scales over which a thermal gradient can be maintained. And we can actually produce maps of this, and that's what's shown in this slide here. So there's a map of surface roughness derived from the diviner data. At this point, we've only really mapped this for the lower latitudes because it's difficult to pull out the emissivity at higher latitudes, which is needed in order to correct this temperature difference. But the point is that you get a range of RMS slopes in the range of about 10 to 30 degrees. And then the histogram is shown in this next slide. So we don't really see any correlation to speak of between the Maria and highlands terrains. Both have peak RMS slopes around 20 degrees. And just for comparison, as I said, larger scales tended to show smaller slopes or smaller RMS slopes, lower surface roughness. And so Meg Rosenberg did this using lower data. And so on this 17-meter baseline, they find slopes in the range of about 5 to 20 degrees. So what scale are we actually looking at here? And what's plotted in this plot is the thermal skin depth over the course of different ranges of time. So the bottom axis here is lunar hours. So 24 hours is on the right-hand side. That's one lunar day. And the three different curves are different values of the thermal inertia of the regolith. So lower thermal inertia means less consolidated, more insulating material. And so what we've done is we've taken eclipse cooling measurements with diviner and just watching how the lunar surface cools over the course of the eclipse. And we find that the typical values are around 10 SI units in thermal inertia. So that's the middle line here, it's the dashed low line. And so what this means is that the maximum penetration depth for one of these diurnal thermal waves is roughly 10 millimeters, about a centimeter. And so what this means is that the minimum size of a cold trap you'd expect is going to be roughly on this scale. So you can expect cold traps as small as 10 millimeters. So what we did then is to take this slope distribution and calculate temperatures for every different combination of slope and azimuth, and then plot histograms. So that's what's shown in this slide. This is each column represents a different value of the RMS slope, going from 5 to 15 to 25 degrees, and then each row is a different latitude. So here we've got the equator, 45, 60, and 85 degrees latitude. And what's shown here are the annual maximum temperatures, and that's the dashed lines, and the solid lines are the annual mean temperatures. And for comparison, the two vertical lines show the two cutoff criteria that we're using, 106 K for stable surface ice for the maximum temperature, and 145 K for subsurface ice. And so you can see starting at around 60 degrees latitude, depending on the slope that you use, you'll start to pick up some subsurface ice, and then at higher latitudes you get stable surface ice in these little cold traps. The next slide is something similar, but just focusing on the higher latitudes. So this goes from 75 to 90 degrees latitude now. Same RMS slopes. And you can see here that at these higher latitudes, you get a substantial fraction of the lunar surface where you would expect ice to be stable either at the surface or in the subsurface. I'm not going to dwell on that because I think this next slide illustrates it more clearly. So for two different values of the RMS slope, this is as a function of latitude, the fractional surface area that we'd expect ice to be stable either at the surface or in the subsurface. The solid lines are stable subsurface ice, and the dashed lines are stable surface ice. And so you can see, depending on the value of the surface roughness that you choose, the subsurface ice starts to kick in around 65 degrees latitude, and the surface ice starts to kick in around 75 degrees latitude. So we can do this, we can compare this to the neutron suppression regions measured by Lunar Prospector and Lang. The plot on top in this slide is showing this average background epithermal neutron suppression factor. This is from a paper by Bill Blanton. So there's this gradual trend towards higher latitudes, and starting around 75 degrees latitude, there's this sharp increase in the apparent level of hydrogen. And our model predicts that's right around the latitude where we start to see these small-scale cold traps start to become more prominent. And so I think more detailed modeling is needed here, but this at least suggests that these small-scale cold traps could in part be what's causing this background epithermal neutron suppression. And then superimposed on top of that would be these larger-scale cold traps. So just some preliminary thoughts. We've got these diviner measurements that show at small scales below about 250 meters, the average surface roughness is quite high, about 20 degrees on average. And these small scale cold traps are probably less than a meter or about a centimeter at the highest latitudes. And we can constrain that just based on the diviner thermal inertia measurements. And so the temperatures I showed demonstrate that there's this gradual forward increase in ice stability within these little cold traps. And based on these fractional surface areas for the different values of the RMS slope, we'd expect a comparable amount of surface area to be occupied by the little cold traps as the huge ones that we've traditionally mapped with these orbital data sets. So what we really need to do now is to use models like these combined with the diviner and other data sets to really model these transport processes that Norbert Schroedhofer and others have talked about, and how that relates to the way the volatiles are exchanged with the cold traps, and where they prefer to end up. And that's about all I had.
Great, thank you.
Okay, let's see. We have a couple of questions here from Michael Poston. Paul, are these cold traps at the surface or are they buried traps?
So we looked at both. So the surface cold trap criterion we used was 106K. You can do this same analysis for any cutoff you want to use. And then we also looked at subsurface cold traps where the criterion was based on Norbert Schroedhofer's work, which showed that 145K is appropriate for subsurface ice.
Let's see, I think, Dana, did you have a question or were you part of a separate chat?
Well, no, that last one was a question, but it's basically the same as Michael's question.
Okay. Let's see, and then I think you have another one. Is there any information, theoretical, experimental, on the subsurface temperature behavior? The thickness of the topmost insulating layer varies by a few centimeters, as it is considered to be around 2 centimeters in the present model.
Yeah, so we're finding with diviner that actually more of an exponentially increasing density with depth is more appropriate for the lunar regolith, and that constraint doesn't make a whole lot of difference in this analysis, but it's important for other reasons.
Let's see, I believe there is one more. Let's see, I think in quotes, cold trap size decreases with higher altitude due to lower mean temperatures. Can you please explain? I could not find a relationship between them.
Right, so this is basically due to the fact that above a certain latitude, the mean annual temperature, which controls the temperature at depth, decreases. So basically at some point, the thermal emission at the 100K surface is balanced against the flux that's conducted from the mean annual temperature along that thermal gradient. And you can calculate what that length scale is, and it goes down with decreasing mean annual temperature.
All right.